Okay.
So we ended on slide number 25 yesterday. Make sure that you have all this filled in. It seemed like we were going quickly through the ending here. So we're going to start talking about something called the fossil index. And so the fossil index is, it's not going to include every single fossil. There are certain kind of requirements that make fossils kind of part of this or make them a candidate or something useful that could be used. And so we talked about the idea that if you have something that was once living, and that once living thing dies because that's part of the natural life cycle, it's probably going to die. If this is like the surface, it's going to die and it will lay on the surface, right? And then we know that over time it can get covered up by sediment and debris, and then more and more layers can pack on top. And if that happens and it becomes part of a rock layer, sedimentary rock layer specifically, then that item, that organism can become fossilized, right? That's the process. Well, logic tells us that if you have a organism, then you know roughly when it was alive, if you know how old the rock layer is, like the age of the rock layer that it was found in, or vice versa, if you know the age of the fossil by running different tests that we'll talk about, then you can kind of have a prediction of or a rough estimate of the age of the rocks. So they kind of go back and forth. So the living things can maybe help identify the rock age can maybe help identify when that living thing had been alive, right? And so that's where the fossil index becomes useful and helpful to us. So here's some things that are required. To be useful and for a fossil to be part of this special index, it needs to be distinct and easily recognized, right? So these definitely are easy to see. You can pick them out. It's not like you just have this kind of blob or random shape where it could be different types of organisms. So it's something that's very recognizable. It has to have a wide geographic distribution. Right, so meaning it has to be found in multiple locations, maybe multiple dig sites, multiple, just found in lots of different places. Okay, so you have to find a sample of it in each location. But it needs to have only lived through a short period of time, because if it's through a bunch of different times, then that doesn't help narrow anything down, right? So it needs to be specific enough in time that that can be useful information for us. And as we start looking at this will kind of make sense, right? So it has to be easy to recognize, wide geographic distribution, short lifetime. So I think of like wide geographic range, like found in a lot of samples, but in a short amount of time, okay? Not found in a bunch of different layers. Right. And so you really only want to find the fossil in one layer per dig site or per sample location. Okay. All right, so this would be like one sample location, and then this would be another. You can clearly see that there are unique layers. And so these are different rock layers, and they're represented by the different, little dots or lines, right? Trying to show, hey, you're looking at unique rock layers here. Over here, we also have some rock layers. And so we're gonna look and see, there's only one fossil that they're looking at per layer. And so if you look at this one, it kind of looks like a moth. You see it over here as well. You see this little snail looking type thing over here. Now, over here you see a fossil that does not exist, or we don't have a matching layer over here. And it's almost like that layer got scraped away. So from there you could maybe kind of hypothesize or predict, maybe there was some kind of major weathering event. Maybe something happened and it washed that whole layer away, and so anything that used to be here is now gone, all right? Over here, we see 7 and 8, these two fossils in those two layers, but we don't have correlating layers over here. So maybe something remove those, because we're assuming that this would be 4 and 3 would be the same time period. Like if you have the same organism, you would expect that, you know, if it dies out or we don't see it again, that like it didn't come back. Yes.
There's also another layer 1 or 2 on the left side.
Correct. And so again, we don't know exactly why or what happened, why these layers were here and these were not. Maybe there was something that had removed them, just like something that had removed layer 5, or maybe they just didn't get laid down for whatever reason. So maybe there was some kind of major earthquake or some event and it changed the layers that were here, as opposed to miles and miles away, did not experience that same event, right? So do we know for sure what happened? No, but we can make some kind of predictions and some guesses on what we think maybe took place. All right, and so geologic time gets divided up based on organisms within the fossil index. So based on these fossils, it's kind of correlating to like periods of geologic time or time in our past. Okay. And there's something that's called unconformities, and they can be present when there's a gap in the record. So like at 5, at 8 and 7, at 1 and 2, those are unconformities. Un means what? What does that prefix un mean? Good, not. So it's not conforming. Well, what does conforming mean? What do you think, Sarah? Okay, good. Being the same as, or like fitting in with something. So like, you might have heard like, you need to conform with the norms of society. You need to follow the rules, fit in, do what the rest of society is doing, right? Whether that's true or not, like I've heard that quite a bit in my life. And so conforming means just kind of fitting in and doing kind of the expected. So if you see something that is not conforming, then you are getting something that is not what you would expect. And again, Zach's like, well, there's no 1 or 2. I wonder why. Well, that's the big question, right? That is the unconformity of this, right? It's not following the layers like we would expect. All right, so here we have, they're calling these outcroppings. Sometimes you'll see them called samples. These are 4 different locations, okay? These 4 different locations have several different layers to them, and they have multiple different fossils. So our job is, from these columns, we're going to try to pick out the fossil that would be the best fossil to help us date or learn more about that layer based on the fossils that are in that rock layer. Okay, so I think kind of color coding things always helps me visually see what's going on. So I'm going to take my yellow highlighter, and anything that is A, I'm going to circle. All right, so I see it here, here, and let me know if I skip any. Here and here. Let me switch colors and go to B. I think this is a trilobite. I see one here and here. Okay. Let's go to C. It's kind of like a moth. Let's see one here. And then D, okay? So we said the rules that help identify what would make a good fossil to have in the index would be one that is easy and distinct to recognize, which all of these are. Like, it wasn't hard for me to be like, ooh, is it this one or is it this one? Like, it's clear that these 2 are the same and that those 2 are not, okay? So that's pretty easy, right? The second thing is that it has to have a wide geographic distribution, means it has to be seen in multiple or as many sample locations as possible. So we need to see it here. And then the final thing is it has to only have lived for a short amount of time. Well, the short amount of time means it's only found in one layer, not in multiple layers. So we're gonna go through these and see which ones seem to match. Were you gonna answer?
Yeah.
Okay, just hang tight and see if you're right. All right, let's just start over here with D. All right, so it is distinct, they're all distinct. Do we see it in all samples?
No.
No, so right from the get-go, D is not good. It was only in one layer, but it's only in one location also. It's not widespread in multiple areas, okay? So let's go to the red, C. Well, I do see it in all of my locations. So that's wide geographic distribution, which is good. All right, so red is so far still in the running. Next thing is we need to make sure that it's only seen in one layer for every sample. So it's only in one layer. It's only in one layer. Ooh, it's in all the layers here. Because of that, it doesn't help us narrow it down anymore. This one was good, these two were good, but because in outcropping or location 2, it's in all the layers, that doesn't help narrow it down and doesn't give us enough specific information. All right, so C is out. Let's look at B. I see it here, 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 and here. So it reaches all 4 outcroppings, meaning it has that wide distribution. Okay, so far so good. Do we see a problem with the green? Zach, what's wrong?
There's multiple in each outcrop.
Yeah, so there's 2 here, 2 here, 2 here. This one had 1, but the rest kicks it out. Okay, it's not going to be the most helpful. Might be A. Sarah, is that what you were thinking? Let's check it. So A, we need it in all locations, check, and we need it in only 1 layer per location. Yep, 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 yep. All right, so this one will help us. It will let us know if we can date the age of this fossil, then we know the age of this rock layer, or vice versa. Okay, so this kind of walks through what we just did. So B and C are found in several layers. They existed through too much geologic time, so too many layers, right? D was only in 1 layer and only in 1 column, so doesn't have that geographic distribution. And A is going to be the best because it is in all 4 samples or outcroppings, and it's in only 1 single layer per outcropping. I have another song today that you guys are going to love. I forgot how many good songs were in this unit. Fitting song for a Friday, so I'll make sure we stop quick enough so that we can listen to it today. Perfect Friday song. All right, so it's not really, that hard. You just have to kind of go through your checklist. Most of the time, they're going to be unique and distinct shape, right? So really it comes down to, are they in all locations and are they just living in that short period of time or found in 1 layer? All right, so kind of going back to evolution, through the fossil record, we've been able to see evolution kind of changing. And all evolution is slow, but when we say fast, it's still slow, okay? If we say slow, we mean really, really slow. So don't think we're talking like, 1 generation if we say fast. Like it's still multiple generations, or hundreds, or even hundreds of thousands or millions of years for the evolutionary process to take place. Because think about it, our Earth is 4.6 billion years old, right? So a couple 100,000 years is not much. Even 1 million years is not much in the scheme of our Earth's age. So in the fossil record, we should observe evolution that has like natural progression if it's slow and steady. So we'd expect to see something that we call transitional forms. Forms that transition slowly over time. So you don't just go from one thing straight to another. There's going to be some intermediate type phases involved. And if there should be records within our fossil index that kind of support this. So if this is where we start, you see that time, and we'll talk, the oldest layer is always on the bottom, and the youngest layer of rock is gonna be on the top, and we'll talk more about that shortly. So if these are the oldest, they don't just go straight from this to this. First they're like this, and then they get these little lines, and then they get these little spikies, and then the spikies turn into kind of like flagella that look like mobile and, you know, more, not, I guess, less rigid, right? And so we have this transition. We have this transition in between this and where we are now, okay? And so that's all this means, that if this is slow and steady, you're gonna see those intermediate type phases. Okay, and so even if we go, you know, looking here, right, slowly the legs get shorter and shorter until they become fins, the body angle kind of changes, right, and so you don't just go straight from this to this. This would be a jump. You'd be like, well, how did it get there, right? Yeah.
What is that at the bottom?
I don't know.
What the world?
We're assuming things became a lot more aquatic, right, and it became more of an advantage to be able to maneuver in water and then like fully submerging by the time you get here. So yeah, I'm not exactly sure what that is. So maybe if you look up like the ancestors of the dolphin or porpoise possibly. Okay. And so fossils or organisms that show these intermediate states between the ancestral form, which is the old, and then the descendant, which are the generations that follow, are referred to as transitional forms. And there's a lot of examples of this. This isn't something that like I'm just making up. There is a lot of proof of this. So there's something called the Pakicetus, and it is an ancestor to modern whales. And so the Pakicetus were actually land mammals, and it's clear that they were related to whales and dolphins based on a number of specializations of the ear. Right, so even though that picture was showing more the dolphin, maybe, you know, that original critter that we were looking at was the Pakicetus.
That doesn't look like a dog.
Possibly.
Looks like a
And so we have the skull of the gray whale today, right here, that is in our oceans. It has a nostril that's on the top of its skull. And it would appear from these two species or specimens that the position of the nostril has changed over time. So if the Pakicetus had the hole on the front at the tip of the skull and the gray whale had it at the top of its skull now, where would you expect, if we could see evidence of a transitional form, where do you think that hole was during that transitional phase?
like right here.
Okay, so kind of like more in the middle-ish. And actually, there's an antecedus, which has exactly that, right? So it goes from the tip, moving upward, and then finally where it is today. Where will it be in a million years? I don't know. Maybe like all the way back here, or maybe it stays that way. I don't know. And so that's the thing. You can't really predict how something is going to change. It's just kind of looking at how it has changed and maybe at the environment. Maybe there's some reasoning why that became an advantage for these antecedus to have the hole there for their nostril versus here. And then those became more dominant, and that's the trait that got passed on, right? And then slowly over time, you know, there were some random variations, and the nostril hole was more at the top. And for whatever reason, that was an advantage. And so they became more dominant, and that became the kind of the branch of the species that became more dominant and got passed on to future generations of the gray whale today. But does that make sense, having those intermediate type transitions? Good. So last year I taught a 6th grade transitions class as one of the specials for the 6th graders to help them transition into junior high, going from an elementary student to being a junior high student as a 7th grader, right? Helping them be familiar with the building and kind of our scheduling and understanding expectations, trying to help them transition from being an elementary student to a junior high student, because it can be a big jump, right? And so that transition is kind of that in-between form or in-between period to try to help move into another stage. All right, and so sometimes this can happen fast, like, and again, when I'm saying fast, it's still really slow. But there can be big jumps, all right? So we're looking for like big, quick jumps where you don't see those transitions. It's just like you go from one thing, and my guess is that the environment would have had to change, something drastic would have had to happen to make a variation that an organism had that was very different from its, current population. That advantage would become that variation would become a big advantage because something drastic had changed. And we talked about some of those ways that things could change quickly. And so that's my interpretation of why you would have a rapid change and you wouldn't see that transitional form. There wasn't time, like you had a feature that was helpful and that trait made that particular group survive and then it got passed on. You didn't have this over time. And so this is the same example, but now we just go straight from one to the other. We don't have the little lines and then the little spikes. We go straight from here to here. Okay, same kind of idea. Okay, all right, so if I look at this, looking at these two branches, these two kind of groups here and then here, yeah. So which image do you think shows slow and steady evolution, and which one do you think shows rapid? So slow and steady, you're going to see transition. Rapid, you're going to see just kind of big jumps. All right, what do you think, Jonna? Is going to be which one? Okay, so you like the slow and steady. You guys like the slow and steady on the right? Slow and steady on the left? We have some argument.
Well, that one shows different parts in the wings.
Okay, good. I like it. I can see you guys really looking at it and kind of being like, Sarah, what do you think? The what? Okay. You think the quick jumps is on the left? 9?
I think the quick jumps are on the right.
All right.
We go from pattern to straight to nothing.
Okay. What do you think?
This is slow. This is fast. Yeah.
Okay, so let's see. Oh, I'm sorry. You never get to know.
Spaghetti.
I know. Let me click over here. All right, this is actually going to be our slow and steady. It is kind of hard, like when you're looking at this isn't quite as obvious as like looking at this one being like, oh, I see no transition. And then this one being like, oh yeah, like I see you have these in between, right? So if you're looking at this and our slow and steady, it's not as drastic, okay? You have little changes. It's not like you have one thing and then you have another. So this mixed went from mixed to all light or pretty much all dark, okay? And so I don't think this is a great example because I think it is a little bit easier with those other examples we were looking at. But it's going to be in between. You're going to see some transition. You're going to see, a little bit before you get a change. So going from the mixed, it takes a while to get where it's all separated and it's all solid. Okay, here you have mixed. Next thing you know, you have solid. All right, so fossils age. We're going to talk about two types. There's two types of ways. One is with relative dating. Relative dating, and I do not mean you are dating your cousin. Okay?
Alabama.
I know, you guys are already laughing. Poor Alabama gets a bad rap. Every year it's always like, I ain't from Alabama, I ain't dating my cousin, right? I hear it. You guys did it yesterday, the other day? Yeah. And like, yeah, you guys up here were. So I just kind of smile because every time I say relative dating or you read it, it's always like instant, or Kentucky gets a bad rap. So I have a lot of friends in Kentucky, so like I like harassing them anyway, so that's okay. I personally don't know any Alabamians, so don't know if they deserve it or not. Okay, so relative dating is just an estimate. We do not assign an exact age to the fossil. It's a comparison. So it's understanding the age of this layer and the age of this layer, and then you have a layer in between, and so you know, okay, it's younger than this, but it's older than this because it's kind of in the middle. All right, so it's more of a comparison. That's the relative part of it, not relative meaning family. It's relative meaning a comparison. If I say relative to summer, it's really cold right now. Relative to winter, it's really warm right now,
Yeah.
right? It's what are you comparing it to? It's almost kind of like that frame of reference that we talked about in a way, right? So when we talk relative, we're talking comparison. And so this is a huge idea. The oldest layer will be found on the bottom, right? The newest layer is going to be at the top. You're gonna keep burying layers and covering them up, covering them up, covering them up. So the youngest is going to be, the most new is going to be at the top. The oldest is going to be at the bottom. Here's the way I think about it. So when my son lived at home, he was messy. Okay, it just happens. And so every day he'd come home, take his school clothes off, and like they'd be in a pile, right? There's Monday's clothes. Tuesday, come home, pile on top of Mondays. Wednesday, come home, pile them on top of Wednesday, or on top of Tuesdays, and then Thursdays on top of Wednesdays, and then Fridays on top of Thursdays. You get what I'm saying?
Mm-hmm.
Okay, so he'd have it like all piled up in a corner. So if he needed something, so like let's say on Monday, his teacher gave him a Jolly Rancher, right? He was saving it for later, and he put it in his pocket, and he totally forgot about it. Took his clothes off when he got home, like, right? Threw them on the floor. They were at the very bottom. Friday comes around, and he's going to grab all of his laundry and take it downstairs, and he remembers, oh shoot, I forgot, I got a Jolly Rancher. Would he have to dig through the whole pile to find that Jolly Rancher?
Yeah.
If he remembered that he had it and got it on Monday, would he have to dig through the whole pile?
No.
Go to the bottom, right? And so if you know when or like the age of something, the age, 5 days ago he got that Jolly Rancher, then he could go straight to that location. If he had just gotten it on Thursday, then you could just go to the top of the pile, right? Yes?
In that photo, why is the others like cutting through?
Good question. So there is something called an intrusion. Doesn't it look like that rock layer is intruding into these layers? Like it cut right through it? What's it look like to you?
It's just going through it. It's just like sitting there.
Okay. So what happens is there is magma, obviously, in our asthenosphere. Sometimes it can squish its way into rock layers. And sometimes it will actually form these intrusions that are pretty like contained. And so they can just like cut right through all the layers. Notice how it says that it's the youngest. These layers had to be there before the intrusion could intrude, is the way I think about it. These layers all had to be there. And then I'm sorry to do this with food. My favorite donuts are the Long Johns that have the cream in them.
Mm-hmm.
You can't put the cream in the middle of that donut if you don't have the donut, right? If I just, like they take their little tool and if I just do that, then it's just cream. It's not the donut, right? So these layers have to be there, just like the donut has to be there before the cream can be inserted into the middle of that donut, right? Think of a bank. Bank robbers go to an empty lot and they decide to break into the bank. And they go to the lot and there's no bank. Can they intrude? Because that's what a robber is. They're called intruders. Can they intrude on a bank that's not there?
Yeah.
No. Right? So the bank physically has to be there before the intruders can intrude. And that's the way that I think about intrusions. The layers have to be there before that magma can come up. And we'll look at some other examples that are going to show what happens if it reaches the top and like some different views of it. Here's the other type of dating. This is absolute dating. And I think, Zach, maybe you asked about this. Somebody did. What is radiometric dating? Is it different? it is the same as absolute dating, right? That we give it two names. Absolute is more accurate than relative. It is not a comparison. It is looking at radioactive elements that are decaying inside certain rocks. And if we can date that material, then we can have a good idea of how old the fossil was when it was living, and then when it died and got put in that rock layer. And we'll look at that a little bit more, but just understand absolute dating is more scientific, it is more accurate, it's obviously more expensive, it's harder to do, and it doesn't always, some of the samples it doesn't always work with because they're not radioactive. And so if they're not radioactive, then you can't use this method. When we're saying radioactive, it's not always radiation that is harmful either. Okay, so keep that in mind. And so each element is going to do this at a different rate. And if there's like a formula that they use to determine how much of the radioactive material is left. And based on that, they're able to determine how old the sample is. And we'll get into that a little bit more. But these are the two ways that we can actually date fossils. So let's stop there and listen to our song.